Dear friends, I am Dr. Santosh Desai and I welcome you all to my YouTube channel. Today I am going to discuss properties of Laplace transformation. So under these properties, I am going to discuss linearity property, first shifting property, second shifting property and change of scale property. Now to prove these properties, I am going to use definition of Laplace transformation only. So let us see one by one. So the first one, linearity property. This property already we studied for the derivative and also for the integration. That is, for example, if you have the function just u plus v, the derivative of u plus v is nothing but derivative of u plus derivative of v. Similarly, if a is constant and u is function, the derivative of au is equal to a into derivative of v. That is nothing but your linearity property. So let us state first, if a and b are constants and f of t, g of t be functions of t, then Laplace transformation of a into f of t plus b into g of t is equal to. So the value of this function is equal to, this is a into Laplace transformation of f of t plus b into Laplace transformation of g of t. So that is, if the two or more functions are separated by plus or minus sign, then you can take the Laplace transformation of each function separately. So that is the meaning of linearity property. Now let us see the proof for this. So just we consider LHS and I will try to prove for the RHS. So I am going to use definition of Laplace transformation only. By definition, Laplace transformation of a into f of t plus b into g of t is equal to. Now just I use the definition. So as we know that Laplace transformation of f of t, this is 0 to infinity e raised to minus st f of t dt. So this is the definition of Laplace transformation. By using this definition, so here we get, it is integration from 0 to infinity e raised to minus st and the function is a into f of t plus b into g of t. So this is a into f of t plus b into g of t and integration with respect to t. Now after this I am going to use properties of integrations. So let us multiply e raised to minus st to this bracket. So this is equal to integration 0 to infinity e raised to minus st a into f of t plus e raised to minus st b into g of t into dt. So we get this one. Now again using the linearity property of integrations. So we get this is equal to integration 0 to infinity e raised to minus st a into f of t dt plus integration 0 to infinity e raised to minus st b into g of t dt. So we will get by using linearity of integrations. Now here a and b are constants. So let us take this a outside the integration and b also outside the integration, then we get. So this is equal to, let us take a outside 0 to infinity, integration 0 to infinity, and remaining terms are e raised to minus st f of t dt plus Again here b is constant, so take it outside. Integration 0 to infinity e raised to minus st g of t dt. Now this is the actually this completes the proof. Now just you observe this integral 0 to infinity e raised to minus st f of t dt is nothing but Laplace transformation of f of t plus. Similarly here this integral is also the Laplace transformation of g of t. So here we get this is b into Laplace transformation of g of t. So thus we proved Laplace of a into f of t plus b into g of t is equal to a into Laplace of f of t plus b into Laplace of g of t. That is, when two or more functions are all separated by plus or minus signs, and then the Laplace of that function is equal to Laplace of each function separately. So that is the linearity property. So this property is proved for only two functions f of t and g of t. So one can generalize this property for n functions. So as a note, so if a1, a2 and so on an are constants and f1t, f2t and so on fn t are functions of t, then Laplace transformation of a1 f1t plus a2 f2t plus and so on plus an fnt is equal to, this is equal to, you can separate each Laplace, so you get a1 into Laplace of f1t plus a2 into Laplace of f2t plus and so on plus an into Laplace of fn of t. So that's it. So this is the linearity property for functions for n functions. So this is our first property, that is linearity property. Now let us move to the next one. Let us consider first shifting property. So let me write first statement and then we will go for the proof. So the first shifting properties. So again let us take a statement for this. If Laplace transformation of f of t is equal to f bar of s, then Laplace transformation of e raised to at f of t is equal to f bar of s minus a. So let us consider the proof for this. Now first, before that, the question is, what is the use of this property? So this property is useful to find out the Laplace transformations of product of two or more functions when one of them is exponential. So just listen carefully. This property is useful to find out the Laplace transformations of function which is product of two or more and one of them is exponential function. Then you can use this first shifting property. And again, how to use the first shifting property? So when we want to find out the Laplace of some function and if that function contains exponential term, you first skip that exponential term or neglect that exponential term and find the Laplace of remaining function f of t. Let us assume that Laplace of f of t is equal to f bar of s, and to obtain the Laplace of this e raised to at into f of t, you just replace s by s minus a in the Laplace of f of t. And here it is clear that why this is called as a first shifting, because we are shifting s to s minus a, and therefore we call it as a first shifting property. So let us consider the proof for this. So one can prove this property from LHS to RHS or from RHS to LHS. In both ways one can prove this. So let us consider here from LHS to RHS. So again I am going to use definition. So by definition, Laplace transformation of e raised to at f of t is equal to, just after the definition once again, so it is 0 to infinity e raised to minus st e raised to at f of t dt. Now here two exponential functions are there, so you simplify this and we get this is equal to 0 to infinity e raised to minus st plus at f of t dt. So this is equal to again integration 0 to infinity e raised to minus s minus a into t f of t dt. Now here let us take s minus a is equal to p. Since s is a parameter, a is a constant, and let us assume that s minus a is equal to p. So this is equal to integration 0 to infinity. Here you will get e raised to minus pt, and this remains as it is, f of t dt. Now you just observe this integral. This integral is nothing but our Laplace transformation. Since as we know that, let us take this one. Laplace of f of t is equal to 0 to infinity e raised to minus st f of t dt. And this is again we are denoting by f bar of s. So let us observe these integrals 0 to infinity e raised to minus pt f of t dt, and here is e raised to minus st f of t dt. We are denoting this integral by f bar of s. So there s is parameter. Now here p is parameter, so therefore its value is equal to f bar of p. Its value is equal to f bar of p. But what is p? P is nothing but your s minus t. So this is equal to f bar of s minus t. So finally we will get the result. So e raised to Laplace of e raised to at f of t is equal to f bar of s minus t. Similarly, we can prove another one. So I will take it as a note. So here, if Laplace transformation of f of t is equal to f bar of s, then Laplace transformation of e raised to minus at f of t is equal to, I need the value of this Laplace transformation. So one can observe that whenever we are multiplying f of t by e raised to at, you have to replace s by s minus a. Now here, whenever we multiply f of t by e raised to minus at, we replace s by s plus a. So its value is f bar of s plus a. So these are the first shifting property. Now next we consider second shifting property. Let me write the statement first. So let Laplace transformation of f of t is equal to f bar of s, and one function is defined, g of t is equal to, this function is defined in the form of f of t. So its value is equal to f of t minus a whenever t is greater than a, and its value will be 0 if t is less than a. If this is the case, one function is given, its Laplace transformation we know. One more function is defined, and this function is defined in the form of original function f of t. So its value is equal to f of t minus a whenever t greater than a, and it is equal to 0 if t is less than a. Then Laplace transformation of g of t is equal to. Then we can find the Laplace transformation of this function, and it is equal to e raised to as into f bar of x. So this is the second shifting property. Now I am going to prove this. So again, for the proof, we need the Laplace of g of t. Function is defined, two parts are there, and we know the definition. So by definition, Laplace transformation of g of t is equal to, just we write the definition first. It is 0 to infinity e raised to minus st g of t dt. But the function g of t is defined into two parts. One is t greater than a and one is t less than a. So you have to split this integral into two parts. So here we get 0 to a e raised to minus st g of t dt, plus one more is a to infinity e raised to minus st g of t minus a into dt. You will get this one. Now here one can observe that in the interval 0 to a, that is t less than a, the value of the function g of t is equal to 0. So therefore the value of this integral will be 0. Now you just remains with only this integral a to infinity e raised to minus st, and the value of g of, here it is g of t, and the value of g of t is equal to f of t minus a in the interval a to infinity. So just I substitute the value of g of t here. So this is equal to integration a to infinity. Here you will get e raised to minus st, and g of t, its value is equal to f of t minus a. And here you get dt. Now you have to simplify this one. Now here we can use the substitution t minus a. So put t minus a is equal to x, and from this one can find the value of dt. So this implies dt is equal to dx. Again here the limits a to infinity, these are the limits of t, but we are changing variable to t to x, so therefore we find the corresponding limits of x. So just we use this relation and find out the values of x. So when t is equal to a, we get x is equal to 0, and when t is equal to infinity, we get x also equal to infinity. So substitute these values in RHS, so we get. So thus Laplace transformation of g of t is equal to, limits will be 0 to infinity, because when t is equal to a, we are getting x is equal to 0, that is 0 here, and t is equal to infinity, the value of x will be infinity, and here we get infinity. Substitute all the values. So here we get e raised to minus s, and the value of t is a plus x. It is a plus x. Then it is, here you will get f of x into dx. So you get this one. Now this is equal to, this is equal to. Now you just simplify this. So here you get 0 to infinity e raised to minus sa into e raised to minus sx f of x dx. This is equal to e raised to minus sa, because this e raised to minus sa is independent of x, so you can take it outside. 0 to infinity e raised to minus sx f of x dx, and this is equal to. Now here you can observe this integral. This integral is nothing but Laplace transformation of f of t, and Laplace of f of t, or you can say Laplace of f of x, that is equal to f bar s. So here we get e raised to minus sa into f bar of s. So we get the this second shifting property. There is a one change. So here we need it is minus. So Laplace transformation of g of t is equal to e raised to minus as into f bar of s. So this is the second shifting property. And now finally let us consider change of scale property. So for this, statement is let Laplace transformation of f of t is equal to f bar of s, then Laplace transformation of f of at is equal to 1 upon a into f bar of s upon a, where you put the condition a is strictly greater than 0. If a is negative or if a is equal to 0, then this property not holds. So therefore, let us take a is strictly greater than 0. So let us prove this one. Again we start from LHS, from the definition. So by definition, Laplace transformation of f of at is equal to, just use the definition again. So it is 0 to infinity e raised to minus st f of at into dt. Now you have to simplify this one. So again one can use substitution at. So put at is equal to u. So this implies t is equal to u divided by a, and therefore dt is equal to 1 upon a into t. But these are the limits of t. So we find the limits of u. So when t is equal to 0, we get u also equal to 0, and t is equal to infinity, we get u is equal to infinity. So substitute these values in this above integral, and then we get so Laplace of f of at is equal to, so just we put the values. Integration 0 to infinity. So the value of t we know, that is u upon a. So it is e raised to minus s, it is u upon a, f of u, and the value of dt, that is 1 upon a. 1 upon a into d. Just to simplify this, you will get the required result. Now, simplification. So here, 1 by a, you take it outside. 1 by a is the constant term, so you take it outside first. Then, this e raised to minus s u upon a can be written as, let us check this one. E raised to minus, this is s upon a into u, f of u into d. Now, we use the definition. So as again we know that Laplace of, let me write here in terms of u, Laplace of f of u is equal to 0 to infinity e raised to minus su f of u du, and this is equal to f bar of s. So you check the terms and the value of this integral you will get. So 0 to infinity e raised to minus su f of u du, its value is equal to, you have to write this parameter here. So use the same thing, then you will get this is equal to 1 upon a f bar of s divided by a. So this is the change of scale property. So these are the 4 fundamental properties in the Laplace transformation. So in the next lecture, we will see some example based on linearity property, first shifting property, second shifting property, and change of scale property. For more videos, please subscribe my YouTube channel, and thanks for watching. Bye.